Feliciano Giustino talking about many-body electron-phonon.
Okay, can you hear me up there? Okay, cool. So today what we're going to do is to discuss a little bit more theory about electron-phonon interactions. Okay, so the plan is to go beyond what we discussed yesterday. So yesterday was a very elementary introduction, and now we're going to go for some methods that are a little bit more advanced. Okay, so these are many-body methods. So this is not the whole story. So the story is much broader than what I'm going to describe now, but I think this will give you an idea of the kind of language that people use to discuss electron-phonon interactions in a rigorous and systematic way. Okay, so this lecture is something you need to consider as a taster of what people use in this kind of community. So what I'm going to discuss is basically why one needs to go to a many-body formulation of these things. Okay. Then I will introduce the many-body Hamiltonian that most of you have seen many times, but I will explain what are the challenges that to do with phonons. Then I will introduce the Green's function. So this is really the core of all many-body methods in a way. So it's basically the soul of field theory. So we need to know what that is. And then I will move to the electron-phonon self-energy, which is something that you can calculate with the codes that we discussed during these days. And I will conclude by discussing things like what people call the electron-phonon coupling, so the number, okay, which is more technically called the mass enhancement parameter, right? So all of this comes from these Green's functions approaches. So to start, yesterday we discussed a little bit the Kohn-Sham Hamiltonian, so we take it from there. So to be consistent, so the key message yesterday was that you can do electron-phonon interactions using elementary perturbation theory once you realize that the self-consistent potential is a parametric function of the atomic positions, right? So that was the starting point. So actually, this statement is not trivial and has three implications or three, let's say, assumptions behind it. So the first one is that we already made the Born-Oppenheimer approximation. Okay, so whenever you do DFT calculations, the Born-Oppenheimer has been made already, right? So and that's a pretty brutal approximation. So the second problem is that here there are atomic positions in the potential, but not in the wave function. So that means that the atoms are being demoted from quantum particles to classical particles. So that's a second problem. And the third one is that obviously, since you all know about DFT, you know that all the calculations you do depend on the exchange and correlation functional. So that also means that the electron-phonon interaction depends on the choice of electron, exchange and correlation, right? So that's a bit of a problem because we don't have an exact reference. So we don't know what is the correct answer. So which functional should be the best one at describing electron-phonon physics. And that's really intrinsic to the fact that one starts from density functional theory, okay? So the idea now is to try and go back and do something a little bit more general and see, what are the most general methods one can employ in this area. And at the end of the day, in practice, one keeps using DFT, but knowing where to place the wave functions in the eigenvalues and knowing what are the approximations that one is making, okay? So let me show you a couple of examples where these approximations fail quite miserably. So this is something called a photoemission spectrum. So angled result for the photoemission spectrum of strontium titanate. I'll tell you what is the left plot first. So this is basically an image of the electrons that come out of a sample when you illuminate it with synchrotron light. Okay. So this is the energy on the vertical axis and the momentum on the horizontal axis. So that's basically an experimental band structure. So what one would expect if you were to do a DFT calculation is to find essentially a little parabola here, which is the bottom of the conduction band after a little bit of doping. And you see that there is a lot of more structure that we would not expect. So usually experimentalists, when they find this, they try to analyze it in detail by enhancing the features. So you can see that there is some kind of feature here, maybe something here, maybe something here. So they take the second derivatives of the entire figure. So that's called a curvature map. And then they plot that. And when you do that, you see more clearly some of the features. So the first feature is the conduction band bottom, is this little parabola here. So that's exactly what you would obtain by doing DFT calculation, okay? So you do DFT, you dope it with a few electrons, and you see a little parabola in the conduction band. But then you see also another feature here, maybe another feature here, another feature here. All of these things just do not exist in DFT calculations, all right? But they exist in experiments. So for some reason, we are missing them. And obviously, if I'm discussing them, is that they relate to electron-phonon interactions. Okay, so these things require a many-body approach. The second, maybe most spectacular thing is that superconductivity. So this is an example of 2D superconductor niobium disulfide. So niobium disulfide is a metal. Okay, so if you go plotting the density of states, electronic states around the Fermi level, so that should be something that kind of almost constant if you move by a few millivolts, right? And yet, if you do an experiment at low temperature, you find that instead of being a constant, the density of states has a gap in the middle. Okay, so if you do a DFT calculation, you don't find a gap, right? So this is the superconducting gap, and that is basically the what causes all the properties of superconducting state, zero resistance and all these things. So that is very simply missed by the approximation that we discussed yesterday. So superconductivity we'll discuss in detail, tomorrow by Roxana. So I'm not going to go into that, but this is just to say that DFT and doing perturbation theory on the Kohn-Sham equations very often is not enough to discuss electron-phonon physics. Okay, so we need something a little bit more general, and the starting point for being more general is to go back basically to the Schrödinger's equation for all the electrons and all the nuclei. That's basically the plan. So this is the standard Schrödinger equation you see in all introductions to atomistic calculations. I put all the terms in color. So the red will be the electronic part, so kinetic energy of the electrons, and the Coulomb repulsion between the electrons. So V is just the Coulomb potential. Blue is the part corresponding to the nuclei, kinetic energy here, and then the Coulomb repulsion between the positive nuclei. And then there is one term in magenta, which is the interaction between electrons and nuclei. So that's a negative Coulomb energy, so it's the attraction, right? So that's something very, very simple. So now there are a couple of problems with this expression, and the first one is that this wave function depends on all the coordinates of the electrons and the nuclei. So even if you wanted to solve that, that would be extremely difficult. So one could say, for example, that yes, we do have methods to solve this. There is quantum Monte Carlo one could use, but actually that's not true when you talk about electron-phonon interactions. And the reason is that quantum Monte Carlo solves a problem at fixed nuclei. Again, Born-Oppenheimer approximation, classical nuclei. So the wave function is only a wave function of electrons, right? If you were to also put the nuclei inside, so that would be a multi-scale problem because the wave function of the nucleus is much narrower than that of the electron. So you need grids that are very, very different, and that's very complicated. So not only that, but if you put nuclei inside, you can no longer say that the wave function has to be antisymmetric like a fermion because there are nuclei in the middle. And the spin of the nuclei depends on the nucleus. And therefore, you no longer have a very clear separation between bosons, fermions, and things like that. So this is really problematic. And essentially, what I want to make as a point is that one should really start from somewhere where you need to treat both things on the same footing. And in practice, this cannot be done by using the many-body Schrödinger's equation. So nobody has ever done that, and I don't think it's going to be done anytime soon. So what people have done in the past 70 years is to employ techniques from quantum field theory in the case of solid-state physics, and that has been working, beautifully, and that's why we want to discuss these methods. So I'm going to basically discuss, in 2 slides, what these techniques are, just to show you that there is nothing to be afraid of. It's actually quite simple if you look carefully at it, and it's also very, very elegant. So the first observation, so if you forget the nuclei, let's just imagine a wave function of electrons. The first observation is that one could take the Kohn-Sham wave functions of a solid, for example, build a slated determinant out of that. So that's always something we can do. And I'm going to call that determinant like not dot sub Kohn-Sham, so just a possible determinant. So that is not going to be a good representation of a electron wave function because it's too simple as an object. But I can always do the following operation. I can take away an electron from the valence and place it in the conduction. There's going to be another determinant, and that's what is called in quantum chemistry a single excitation. So this operation mathematically is done using these 2 operators, so C and C dagger. So C here, what it does is to remove an electron, and C dagger adds an electron. So when you look at an expression like that, what this means very simply, it's a new slated determinant where the n state has been removed from the valence and the m state has been added to the conduction. It's just a slated determinant. Okay. So these 2 objects, are just a way to keep a tab on what's going on. So, and then if you can make these determinants, you can also take linear combinations. That's also, a way to construct a more general wave function. Is this the most general? Well, the answer is no, because you can also do something more complicated where you remove 2 electrons and you add them in the conduction. And these are called double excitations. You can also remove 3 electrons of the conduction. So generally speaking, what this means is that you can always write a full many-body wave function exactly as a linear combination of excitations of any isolated determinant, okay? And the advantage of this is that basically you move from the need to discuss wave function of many electron variables to a discussion of the coefficients in these functions and what these operators do, right? So essentially, in field theory, the idea is to move away from real space and go into operator space, and there are many advantages in doing that. So let me show you the key advantage to this. So this is an exercise that you find in any quantum mechanics textbooks. It's usually the first chapter on second quantization. So one can prove that if you have a potential, for example, acting on all the electrons separately, imagine an external electric field, okay? You would have a term for each electron. You can write this as the sum of these terms, which is essentially a C dagger C, so these operators are introduced here, times the matrix element of this operator over standard, let's say, Kohn-Sham orbitals, okay? So these are, very basic results of second quantization. So we're not going to prove it here, but it can be done very, very quickly. You can open any quantum mechanics textbook, you will find this. So why this is interesting? So let me just rewrite this object by using the expression of this matrix element using the Kohn-Sham orbital. So wave function, potential wave function. So if you do that, basically this summation of single particle potentials can be written as these operators here. You find them here, down here. This matrix element is basically the integral of psi m star, v, and psi n. Okay, and then there is a summation outside here. So far it's all kind of just boring, but now if you look carefully, you will see the following. There is a part which is called in red, so summation over n, wave function n, and this operator Cn, right? Then there is another part in blue, which is summation over m, wave function over psi sub m star, and then Cm dagger. So basically that means that the part in red and in blue are essentially identical, except they are one is the Hermitian conjugate of the other. So what people do at this point is to define this sum, to basically give a name to this sum. So this sum with psi m star and psi dagger, I'm going to call it psi hat dagger. And the other one is going to be psi hat. So what these things mean, for example, if I look at here, what this is basically a linear combination of these operators, where the coefficient is the value of the Kohn-Sham wave function at a given point. So this is an operator that depends parametrically on the point where I consider it, right? And the beauty of that is that if I replace this expression here for the red bits and this expression here for the blue bits, I find out that my many-body operator becomes simply an expectation value in a single variable of these two operators, like psi dagger, v, psi. So this is exactly the same expression you would find by, if you were to take the expectation value on a, standard single particle wave function. So the key thing here is that instead of having a variable for all the electrons, suppose you have 50 electrons, it will be R1, R2, R3, up to R50. The expression now has only one variable, R. Okay, so that's a dramatic simplification. So the only price to pay for that is that these objects are not just wave functions; these are operators, right? So one cannot deal with them as just complex numbers, and one has to be a little bit more careful. But this is actually the key advantage of using second quantization. Essentially, one abandons the idea of describing all the electrons one by one and replace them essentially by a description in terms of fields. Well, that's the idea. So how does the Hamiltonian transform after you do this kind of trick? In practice, you will have some kinetic part for the electrons and nuclei, and then the 3 Coulomb interaction energies. I'm not going to write all of them, but I just want to give you the Coulomb repulsion between electrons and the Coulomb interaction between electrons and nuclei because they look very interesting. So first of all, let me just say that if you want to calculate the electron density, you use the same recipe as in single particle quantum mechanics. So in single particle, the density is the square modulus of the wave function. In field theory, is basically the psi dagger psi, where this is the field operator, right? So with these definitions, the electron-nucleus interaction is very simply essentially electrostatic term. So this is Coulomb between 2 points, R and R prime. R is the point where I take the electron density, and R prime is the point where I take the nuclear density. So this is the same that you would find in the first course on electrostatics that you take as an undergrad. So the only difference is that these are not just real numbers; these are actually operators. And then the second bit is the electron repulsion term. Again, So this is a Hartree term, for example. So you have the electron density at some point times the electron density at another point, and then the Coulomb interaction, 1 divided the distance between these 2 points. Okay. So the only complication for the electronic part is that you need to subtract a self-interaction because you don't want the electron to interact with itself at the same point, right? So now this is actually the source of all troubles in electronic structure theory, if you want. So this is the term where things like correlation, exchange, they all happen, all right? But in this language, it looks very, very clean, and then one can deal with that. So the main advantage of all this is to simplify the expressions in order to do maths in a more agile way later. So now I would like to basically go through a few kind of standard tools that one uses in this field. So this page, I'm going to basically do a tiny exercise with you, so to show you how people think in terms of these objects. So first of all, we're going to introduce the, let's say, the energy of a many-body state. Suppose you have a system which is silicon with all the valence bands occupied. You will have, I don't know, 8 electrons. So N here defines the ground state of the electronic system. Suppose that N would be 8 in this case. So H is the many-body Hamiltonian. So we said that when you apply the Hamiltonian, you get the total energy of the system, right? Now imagine adding 1 electron to the system. So it would be, let's say, 9 electrons in this case. So you're adding something to the conduction in practice. And maybe you add not to the grounds, to the conduction one bottom, but to another state higher up. So in this case, the many-body energy, we call it E sub n plus 1 with a, the excitation label S, right? So what people used to define in these cases is something called the excitation energy, which is very simply the difference between these two numbers. Is basically the total energy in the ground state minus, total energy in the excited state minus total energy in the ground state. So notice these are total energies. So this would be, if you do the FT calculation, it would be the total energy, not the Kohn-Sham eigenvalue, okay? So this is what people call excitation energy, or sometimes a quasi-particle energy, things like that, okay? So that's just to establish the language. And now I want to introduce something that is useful to calculate Green's functions. I promised that we would look at Green's functions. So to do that, we need to introduce a time dependence. So when you have these field operators that I gave you in the previous slide, one can make them depend on time by just using Heisenberg time evolution, all right? So this is done by using a unitary evolution of this object. So you have exponential minus I Hamiltonian time over h bar on this side, and the complex conjugate on the other side. Okay, this is standard time evolution. So now let's use this to look at one quantity that is crucial to do these calculations. So that's a simple exercise. So let's consider the expectation value, or let's say the matrix element of this object, taken between the ground state and an excited state. So to do that, basically we take this expression and we replace inside here. So if I do that, basically I have this replacement. It's all kind of simple. So now notice that there is a Hamiltonian here and an eigenstate. So if you apply that, basically this will pop out a exponential minus I total energy E sub n plus 1 S, okay? And then if you do the same on this side, applying to the left, you will have this energy. So when you do this operation, basically you transform these operators into C numbers here, and you can take them out. Okay, so you have basically these two numbers, their difference goes out, and is exactly by definition the excitation energy. So this is to say that this little object I just introduced gives you some kind of overlap here times an exponential that contains the excitation energy, right? So now let's think about this object. So what this is in practice, this is an integral over all the electronic variables. So if you have 8 electrons, it will be an integral over 8 variables of the wave function in the ground state or the excited state. Problem is that these are actually 9 electrons in this example, okay? But this is 8 electrons. So how do you do the integral between those two things? Well, you can do that because this field operator destroys 1 electron on the right, okay? So basically, if you take the field operator times the thing on the right, this actually has 8 electrons now. So you can perform the integral, this would be a number, right? The interesting bit is that this number depends parametrically on this x inside the, so the position inside this operator, all right? So what this defines is really a function of real space. So this function, as a name in the literature, is called a Dyson orbital, okay? So a Dyson orbital, the easiest way to think about it is that this is the cousin of the Kohn-Sham orbital, except that is usually defined for many-body problems, okay? So it contains all the interactions if you were to do things exactly, right? So there is kind of a one-to-one correspondence between Kohn-Sham DFT and many-body methods, and that correspondence comes through, goes through basically these Dyson orbitals, okay? So that's basically the first piece of information. Second piece of information, I told you we need to introduce the Green's function, and I will try to explain the next couple of slides why this is important, okay? So first, I want to tell you what is a Green's function. So this is what is called the single particle Green's function. In this case, it's for electrons. So this is a function of two space-time points, basically position and time here, and position and time. Okay. So imagine, time here, position. So time now, and position here, time in an hour, position here. So this is basically depends on these two variables. And this is defined in the following way. You take the ground state here. So this N is the ground state of your system. Suppose silicon, 8 electrons in the valence. And you basically use that to take a sandwich of these two operators. So first the destruction operator and then the creation operator. Then there is something in the ahead of this, which is called T, is the Wick's time ordering operator. So the way this works is that if this time T is greater than T prime, the operator T doesn't do anything. If this time is smaller than this time, what happens is that it swaps the two operators and it changes the sign. Okay. So this is needed to keep the anti-symmetry of the problem intact. Okay, so it just matters that we don't need to worry about it, just to tell you that it's there. So what this object means, actually the interpretation is very simple and is easy to remember. So if I look at this term in blue here, so what this means is that I have my ground state and this operator creates one electron at the point x prime at the time t prime. Okay, so this means that the state in blue is basically the ground state plus one extra electron at some point at some time, right? So if you look at the left, actually, so forget now the Wick's time ordering operator, just look at the left. So the left thing is actually the Hermitian conjugate of what I just described, except it is evaluated at x and t. So what we can say is that what is on the left is the system, so the ground state with an extra electron at this point and at this time, all right? So the way to think about this, so this is basically a scalar product between two vectors. So the first vector is the system with an electron added at some point in some time. The second vector is basically the same system, but with an extra electron somewhere else at a later time. So what this means in quantum mechanics is basically how much of this state is contained to this state, right? So that's the probability amplitude for finding myself here when I started from this point. So you can think of basically something like adding an electron is propagating somewhere else. So the square modulus of this quantity tells you the probability of finding the electron here. So that's why the Green's function is called the propagator, okay, of an electron or a phonon or something like that. So this function contains a huge amount of information about the system. That's why people like it. And now we're going to discuss a little bit what are the properties and why it is interesting when we discuss electron-phonon physics, okay? So first of all, I want to explain, how it works with a simple example. Suppose that t is greater than t prime. So basically, this time is in the future, and this is, let's say, in the present. So in this case, I said the time ordering operator doesn't do anything, so it's unity, so you can drop it. All right. So now, what we can imagine is that we can place the definition of the Heisenberg time evolution here and here. So this term here becomes this product of three terms. This one becomes a product of three terms. And now you may remember that when I act with the Hamiltonian on the ground state, that pops out the eigenvalue, and the same on this side, right? And also we can notice that these two must commute because it's just a constant times the Hamiltonian. So, they are basically a commuting operator. So that means that I can arrange the expression by having the Hamiltonian here times the difference between t and t prime. And then this operator and this operator will give me the eigenvalue times the difference t minus t prime. Okay, so that's all kind of just a simplification and some maths. So at this point, this looks a little bit ugly still, and it's not very clear what to do with that. But you may remember that I introduced this kind of Dyson orbitals. So there were overlaps between ground state, the field operator, and the n+1 state. So what people do at this stage is the following. So the excited states of the many-body system, they form a complete set of states. So people include the closure relation here and here. So closure relation means I project basically everything on all possible excited states of the many-body system. So what is useful? Because if I now look at this term on the right, this term times this field operator times that is precisely a Dyson orbital. If I look at the left, this term times this field operator times this ground state is also a Dyson orbital. Okay, so if I put things together, what I obtain is that this expression becomes precisely the product of two Dyson orbitals times this kind of exponential with the excitation energy, right? So this is to say that the Green's function actually takes a very simple expression in terms of Dyson orbitals, which is basically a product times these exponentials, all right? So I told you that these Dyson orbitals are kind of the cousins of the Concham orbitals. So you see how this starts approaching the language of DFT. At some point in practice, what is going to happen is that people really use Concham orbitals instead of these objects. But at least we understand where things come from. Okay. So now the next step that people do usually is the following. So you have exponentials with a difference in time. So usually when you see something like that, you start thinking it might be convenient to go into kind of a frequency space. So you do a Fourier transform. So you change the Green's function into something that depends on TNT prime into something that depends on a frequency, all right? So by doing a Fourier transform in practice, what you obtain is something that depends on space, x and prime, and also frequency. And that will be a sum of terms where you have the Dyson orbital in the numerator and the frequency minus the excitation energy in the denominator, all right? So this is one of the most important results about Green's functions. In practice, one can say that if you take the poles of the Green's function in a frequency domain, they give you the exact electron addition or removal energy in the system, okay? So this is exactly the same reason why one uses Green's functions in things like the GW method and things like that, because when we can construct these functions and look at the poles, these poles gives us the many body excitation energies, okay? So we are not bound to use DFT. This can be any kind of theory you want. And the goal here is essentially to try to build Green's functions that are as accurate as possible, then look for the poles, and these poles give you the excitation energies, okay? So this would be so for example, if you want to calculate the band gap, so the excitation energy for removing or adding an electron is exactly what you look for in these poles, and that will give you the many body band gap, okay? So if one could solve for this Green's function exactly, we would have the exact band gaps. Obviously, that's not going to be possible, but at least one can find approximations that are meaningful and also systematic, right? So another thing one can do with these things is that when you have expressions like that, you can take imaginary parts, okay, and that will essentially transform this into a Dirac delta function. So that leads to another quantity, which is called the spectral density function. So I take the imaginary part, the absolute value. So that basically, and I evaluate it at the same point, so x and x instead of x and x prime. So this basically will give you this Dyson orbital square modulus times a Dirac delta function that is picked at this eigenvalue. Okay. So what is this thing? This is basically the density of states of the system. So when you do a plot of the density of states in your system in DFT, you are doing precisely that, except you're not doing it using a many-body technique. Okay. So when people talk about spectral function, what they really mean is spectral density function. That's really is the density of electronic states. Okay, that you can calculate with any electronic structure code. Difference is that in this formalism that actually contains many body effects. So second thing to remember is that from the Green's functions we obtain the spectral function, and then you get the peaks that you need to interpret spectra. For example, photoemission spectra. Then you can use this as a starting point to do optical spectra, scanning tunnel spectra, and all of these things. Okay. So this is to give you a motivation for why Green's functions are important and why this language is very useful. So in practice, what this means is that if one could calculate these things, we could do a lot of comparison, with experiments with the high-level theories. So let me just give you an example of the meaning of these things. Let's imagine that the Green's function has only one pole, okay? And this pole is sitting here in the complex plane. So this is the real axis, this is the imaginary axis, and basically we have an imaginary pole, sorry, a complex pole sitting here. So epsilon is the real part, and gamma is the imaginary part, okay? So if I replace that in my Green's function expression, basically what I find is that some kind of square modulus of the Dyson orbital, in the exponent, I have exponential minus I times the pole, but the pole has a real part and imaginary part. So the real part goes here, so it's just a fluctuating component. Then the imaginary part here multiplies the imaginary unit in the exponential, it was already there. So I obtain something like exponential minus gamma times the time difference. So this object means that this is a function that decays in time, all right? So what this basically tells us that if I place an electron in this point, okay, it's not going to stay there forever. Actually, after a time that is of the order of 1 over gamma, is going to be gone, right? So that's what people call the lifetime of an electron, okay? And this comes directly from the time evolution of the Green's function, right? So that's about the Green's function. If I take the spectral function, what happens is that I need to basically take the Fourier transform of that. And what you can imagine is that this gamma will be responsible for some kind of broadening. In fact, if you take the Fourier transform, the spectral function in this simple example becomes a Lorentzian. So you have a Lorentzian which is centered on the real part of this excitation energy, so here, and as a broadening that is given precisely by this inverse lifetime. So if you look at the spectral density function, the broadening tells you essentially how long an electron can live in that state. So if you take, for example, a free electron gas, so you would have parabolic dispersions. Suppose you switch on many body effects. So what is going to happen, instead of having sharp bands, you have actually bands that broaden, and the broadening in energy is precisely what tells you the lifetime. So you take the reciprocal of the broadening, you get the lifetime of the particle. Okay, and this is something that you observe all the time in experiments, in photoemission, and all these things, right? So that's why we care about these things. So what one goes calculating when we do electron-phone interactions to study lifetimes, massive normalization, all these things, is precisely where more advanced features. But that's basically the general idea. Okay. So just to tell you a bit more about the spectral function. So the example that we have a simple pole actually is not realistic. Usually it doesn't happen. Okay, things are much more complicated than that. So a typical scenario looks more or less like the following. Suppose you start from density functional theory. Okay, suppose you have only one state. You're looking at giving a point. There is only one band, just to keep it simple. So the spectral function will be just a sharp peak, right? So you have a peak corresponding to your eigenvalue. Suppose now you switch on many body interaction. What is going to happen is basically this is going to be messed up a little bit, and usually it looks like the following. There is basically the sharp peak has become a slightly broadened peak. So this peak has moved. So that's what people call in the literature the quasi-particle shift. The peak is also broader, and that's what people call the quasi-particle broadening. And very often, if not always, you find stuff that is not longer in the peak, but is somewhere else. And this is something called an incoherent structure, and is usually associated with some kind of bosons. It could be, for example, phonons, it could be magnons, it could be plasmons, it could be not boson, it could be sometimes electron hole excitations. So essentially, you have more of a potato shape as opposed to have a sharp peak. And this is all the effect of many body interactions. So if you do things like DMFT, instead of something like that, you would have something very broad, and that's actually the effect of correlations. Okay, but these things are very general language to describe all these problems, right? So the question remains, is how to calculate these green functions. Is it possible? How difficult that is. So to do that, I need to basically go back to this time evolution of the field operators. So you remember the Green's function is defined as a sandwich of two field operators. So if we know how field operators evolve in time, we can tell how the Green's functions evolve in time. So what is the time evolution of this thing? So what I can write is the time derivative of this object and see how it looks like. So if I try to do time derivative, notice that I have a Hamiltonian here. So derivative with respect to t will bring down Hamiltonian and then leave this unchanged. Then there will be another derivative where this remains unchanged, and there is a Hamiltonian here coming down, and there is a minus sign. Okay, so that basically means I have a psi times Hamiltonian minus Hamiltonian times psi. That's a commutator, so it can be written this way. Okay, so this is the equation of motion for the field operator. Okay, and it's a standard kind of equation, at Heisenberg equation of motion, that you find these kind of things all over the place in quantum mechanics. So how does it look if you replace the Hamiltonian with the many body Hamiltonian I gave you at the beginning? Okay, so remember we started from all the electrons, all nuclei, and then we rewrote that using the language of field theory. So the beauty of that is that if you try to evaluate this commutator, the expression is extremely simple. You get just a kinetic energy term, depends only on one variable, and you get this kind of a Hartree energy. So this is the density of electrons and nuclei, and this is the Coulomb potential. Okay, so if you look at this expression, so if you look at the left here and the right here, that looks exactly like the Schrödinger equation for a single particle without many body interactions. Okay, under the action of some kind of external potential here. Okay, so this is actually the beauty of many body methods. You abandon the language of many particles and don't talk about just one position variable. Okay, and that's actually the advantage of all of this. Clearly, the complexity, it doesn't go away, and the complexity is hidden in the fact that these are not just functions. This is an operator, these are operators. One has to be very careful with commutation and things like that. So once you have the time evolution of the field operator, you can look at the time evolution of the Green's function. So just a matter of doing derivatives and using the kind of the rule of the product. And if you do that, you obtain something looking like that for the Green's function. So again, you have a time derivative here, some kinetic energy applied to the Green's function. And then the derivative of these objects will lead to some term here that actually is a little bit ugly. So we're not going to go into the details of this, but I just want to mention this is the standard Coulomb that you find also here. So 1, 2, 3, they basically just represent the position time 1, position time 2, position time 3, just to not write a kilometric equation. And the challenge really is in this term, Okay, so this term contains a density, it contains a field operator and another field operator. The electron density, if you remember the expression I gave you earlier, had 2 field operators inside it. Okay, so this is really an expression with 4 field operators, right? So that's the source of all evil in electronic structure again. So this contains basically the R3 term, the Fock term. It contains a 2-body Green's functions, and this is essentially where you find all the nasty correlations that make calculations so difficult. All right. So in other words, all this formula is very interesting, but the complexity of correlation of these things does not disappear. All right. So this is just a way to essentially do bookkeeping and trying to find out where we can do approximations in a meaningful way. Okay. And by the way, this is now general, so it's for electrons, for phonons, for whatever you want. Okay. So one has to specialize a little bit to find something meaningful. So what people have found in the 60s, this is mostly due to the work of Hedin and Lundquist. I mean, probably you've seen that if you've seen GW calculations, is that dealing with that in practice. So if you want to do it the old way, so before the 50s, let's say the very, very old way, here you would find a 2-particle Green's function. Then you can try to write the equation of motion for that. And that basically spits out a 3-particle Green's function. You do that equation of motion for that, 4-particle Green's function. So that's basically successive correlations. That leads to what is called the Born-Bogolyubov Green-Kirchhoff-Yvonne chain that you also find in standard plasma equations and things like that. Okay, it's basically very difficult to solve because you have correlations between more and more particles. So in the 60s, what people found is that maybe there is a way around this, is to redefine this as something that contains a Green's function and something called a self-energy. And the purpose of that is to stuff all the complex into the self-energy and hope that maybe one can take some shortcuts at that point. Okay. So this basically leads to the definition of the self-energy for the electron interactions and the electron-phonon interactions that essentially multiplies the Green's function. And if you want, this is a definition of the self-energy. So by comparing this term with the nasty one in the previous slide, I find a definition of the self-energy. And clearly, all of this is useful only if I can find meaningful and simple approximation for the self-energy. And clearly, if we are talking about this, it means that somebody has found that. So there is a way out of all this kind of complexity. So this is for the Green's function. So how does one go to something closer to Kohn-Sham equations, for example, in DFT? Well, you remember that the Green's function is the product of 2 Dyson orbitals divided some kind of frequency things. All right. So if you replace those expressions and then project on 1 or 2 Dyson orbitals, you are left with something that contains only 1 Dyson orbital. And in practice, this looks like a kind of a slightly more complicated version of the Kohn-Sham equations, where you have a kinetic energy, potential energy applied to the orbital, plus some kind of self-energy here applied to the orbital equal excitation energy times the orbital. So this starts looking very much like the equations we are used to. Okay. So the difference is that we are not starting from that functional theory. We don't have the exchange and correlation potential here. This is a many-body potential that is non-local because it depends on 2 variables. It is frequency dependence because it depends on the excitation energy. Okay, and that is also the complexity of the problem because this potential is evaluated at a frequency that corresponds exactly to this eigenvalue on the right. Okay, so it's a self-consistent problem in terms of this frequency dependence, and this contains all the complexity you can possibly put in a calculation. And from this, you can also imagine why, when you do DFT, for example, you don't get the right band gaps and you have all these problems, because in that case, you basically neglect this frequency dependence. You replace this non-local object by a local object, okay? So there's a dramatic level of simplification there. So you lose many pieces. For example, if you go above standard DFT, you use hybrid functionals, you are kind of going into the direction of restoring some of that because at least you incorporate some kind of non-locality in the functional, all right? But you still don't have the frequency dependence, right? So that's basically where one stands. So at this point, we can start talking about electron-phonon interactions. Where this come from? Basically, you have them coming from the total potential that depends on the electron and the nuclear density, and you have them coming from this self-energy. Okay, so we need to discuss what is the shape of this self-energy to understand how to look into that. Now, let me just give you the equation for the self-energy, and I'm putting this here because some of you might have seen GW methods already. So, and the GW techniques and the Berkeley GW will be discussed, on Friday by the Berkeley GW team here. So this is something that is also basically central to the theory of the GW method, and in fact the equation is identical. Okay, so the self-energy is essentially a product of the Green's function, the Schrödinger interaction between electrons in this case, and a vertex. Okay, so as usual the vertex is very difficult, so people try to neglect it whenever possible. But these two terms are essentially the same that you find in GW. So what is the screening-Coulomb interaction? It is basically the Coulomb interaction between two electrons screened by the dielectric matrix of the system, all right? If you do GW calculations as static nuclei, so that dielectric function only contains electronic screening, okay? So you would have only basically the electronic screening here, and you neglect the part that has to do with the nuclei. If you incorporate also the screening coming from the nuclei, that gives you automatically all the electron-phonon effects, okay? So in a way, the electron-phonon interactions in this story, they come about when you stop neglecting the nuclear screening of Coulomb interaction, you add that to your, let's say, GW problem, and you continue the calculation, okay? So in fact, there's been some discussion in the literature. People say, okay, why don't we use directly the complete matrix to do these things? So we get rid of electron-phonon interaction, we bundle them up with GW methods, and we're done. So there is a complexity with that because typically the energy scales and the K-point sampling required for these two problems are very different, okay? So you cannot just lump them all together because the accuracy needed for one is not the same as for the other. So typically it is better to separate them, handle them kind of in two separate chunks. So just to give you an idea of how the self-energy looks like in more detail, I'm gonna basically show you three diagrams that are actually a schematic representation of how these things look like, and that's something that people use as a language to define this object. And you don't need to know or play with these diagrams, but it's just a mnemonic that is useful to remember. So the first bit is the standard GW self-energy, basically after you do the separation. So this line represents an electron grid function. This line represents the Coulomb interaction between electrons screened by the electrons. And this object here is the vertex, okay? So that's a no-local function. It's very difficult, and typically we neglect it. So if you remove this vertex and you replace the Green's function by the Consham Green's function, you basically get the standard G0 W0 method, okay, that you will see on Friday. There is a second term, which is now incorporated in phonons. So this thing here is an electron line. This wiggly thing is a phonon line. These red bits are electron-phonon matrix element, and then you still have the vertex here, which is the same as for the GW energy, okay? So this is what people call the Fermi self-energy. Is a standard self-energy I will describe in a second with a couple of examples, okay? Then there's one last term that is a little bit strange. It's called the Debye-Waller self-energy, and it has this kind of phonon line folding on itself. So this actually is called a self-energy, but it's not really a self-energy. So to show you where it comes from in a way, maybe I can go back a second. It comes from this term, which is the total potential, okay? Basically, it is something that has to do with the static density of nuclei that in a quantum kind of system is slightly fuzzy, okay? Because you have quantum fluctuations, all right? So that fuzziness gives some kind of change to the electronic properties, and that is kind of taken care by this self-energy. And you have this line folding on itself because basically a Green's function calculated the equal basically point is essentially the density of nuclear fluctuations, right? So this is just to give you some kind of language that you may see in the literature. And what we're going to discuss now is this term, which is probably the most interesting in terms of consequences. So I'm going to basically tell you a little bit about this self-energy. So that's actually what you're going to calculate during the week on several occasions for standard calculation of electron-phonon couplings, for things like superconductivity, for transport. So that's key to all of it, okay? So basically, you need to do a multiplication of the Green's function of the electrons, Green's function of the phonons, and two matrix elements. So the way it looks like, if you take you get rid of the vertex, you will have a square of the electron-phonon matrix element that you've seen yesterday, all right? Then you have some information about the electrons. This is 1 minus F. This is F is the Fermi-Dirac distribution. You find also here information about phonons. This is basically the Bose-Einstein distribution. And then denominators, you have a mix of energies of the electrons and frequencies of the phonons, okay? So they come because you have two self-energies, you multiply, you integrate in time, and basically they basically mix up their energies. So that's basically the standard thing that you may calculate, and this is what basically is implemented in the EPW code when you want to self-energy calculations or relaxation time calculations, okay? So that's basically the general idea. So let me show you one example of this self-energy in action, and this is actually a very old example. This was actually published for the first time, I think, in 1960s by Engelsberger and Schrieffer. They were looking at what happens if you take electron-phonon interactions and you switch them on in the case of a simple metal, okay? And something quite interesting happens. So this is your band structure of a metal, like parabolic electron gas. Imagine you have your Fermi level here. So now we zoom in this range, which supposes of the order of the phonon energy scale. We imagine there being a phonon which does not disperse, just a single kind of mode which is flat, like an Einstein phonon, with a simple constant electron-phonon matrix element. So this is the easiest thing you can possibly do. So if I zoom here, I will basically have this dispersion, which is almost linear because I'm very close to the Fermi level. Okay. Now I switch on electron-phonon interactions. Instead of having this band structure, something changes, and I have this kind of band structure now. Okay. So this is basically the spectral density function resolved in momentum and energy, right? So if I follow the maxima, I basically will find this line. So these are the maxima here, and then the maxima follow this kind of ridge here on this side. So I see that the dispersions have been modified from their original kind of linear kind of slope. And this is very typical of electron-phonon interactions. So what are characteristic things to observe in this case? First of all, this structure appears on the scale of the phonon energy. Okay, your phonon, suppose, is 100 millivolts. You will see this on a scale of 100 millivolts. Then the other thing to notice, which is important, is that here the slope has changed. Sorry, onto the window. Yeah. The slope has changed with respect to this white slope. So that means that your velocity has changed now. Okay. So, for example, if you do this calculation on graphene, you will see that the velocity changes maybe by 10% due to phonons. Okay. So that also changes, things like transport properties. And then you have also this thing that here the dispersion is still very sharp. Okay. But then here they become very broad, so it's really a kind of broad peak. Okay, what is happening in practice is that here the electron does not have enough energy to emit a phonon, but beyond the phonon energy, there is enough energy to basically decay into something with a lower energy and a phonon being emitted. Okay, and that's why the lifetime is much shorter and the peak is much broader. All right. So this kind of thing is completely typical of electron-phonon calculations in metals or 2D materials. And this is an example for a magnesium diboride where this is essentially a measured photoemission spectrum. So the dashed line will be a DFT calculation of the bands. And this kind of peaks here in green and blue is what you see in the experiments. So you see this kind of kicking structure that really is a manifestation of electron-phonon interactions. And this is typically happening at the phonon energy, the most important phonon energy of the system, which in this case of the order of 60 million electron volts. Okay, so these things are not just a theoretical kind of game. It's something that you see in experiments, and they affect the transport properties of systems and other properties that of interest. So now I just want to give you maybe last few slides, very quick summary of the terminology that people use in this context. So all these self-energies can be quite complicated. Spectral function can be very complicated, but usually people like to discuss these things in simple terms. So it is convenient to imagine a situation where your self-energy is quite smooth, okay? So you can do some kind of Taylor expansions. So suppose that when you look at the spectral function, you identify some reasonably well-defined peak, okay? For a given K point, you have a certain energy where there is most of the intensity. So then one could say, okay, maybe I can describe that with a single pole in the complex plane, okay? So it's no longer a sharp peak, but there's a pole in the complex plane. So if I can do that, then maybe I can write my self-energy as a Taylor expansion around that pole. So first term, then a derivative times the distance from that pole and so on, and replace this thing inside this expression. So why people do that? The reason is that once I place it here, the real part of that will basically be combined with the eigenvalue that I start from, and that causes an energy shift on my non-interacting peak. The imaginary part of this object will basically cause a broadening of this kind of line shape, and that will basically be a proxy for the lifetime of my particle. And therefore, it's something that one can discuss in simple terms. And that basically means that I can take the self-energies, look for real or imaginary part, and use those directly to identify some of the changes in my band structures. So in practice, what happens is that usually people rewrite spectral functions in as sum of Lorentzians, and the terms appearing in the Lorentzians are a renormalized energy, which is basically my original energy, like DFT eigenvalue, plus the real part of the self-energy. Okay. Then I have some broadening, which is essentially the imaginary part of my self-energy. And then you see here there is a kind of a Z. Okay, these are what people call the renormalization factor, or the quasi-particle strength, meaning that this object integrates to 1 over the frequency, but it is scaled by Z. So if Z is 0.9, it means that my peak does not contain anymore 1 electron, but only 0.9 electrons. Okay. So usually people say that the quasi-particle approximation is valid where this Z is close to 1. Okay. So in silicon, it may be 0.9, 0.95, something like that. If you go to strongly correlated systems, this may be 0.3, 0.2, so you no longer can talk about a quasi-particle peak, but you are really a very broad line shape that this requires some more careful analysis. And this quasi-particle strength is essentially defined in terms of the derivative of self-energy with respect to frequency. So all these terms are quite important for all kinds of discussions of low energy physics and transport, basically. So just to connect with something you might have heard of is that in many cases, these interactions cause a change of the velocity of the electrons or the effective masses. Okay, and this is something that is useful when studying, for example, semiconductors and transport. So one can define a change in mass as basically a renormalization, which is suppose that the new velocity is original velocity like Consham divided by 1 plus lambda. So this is the famous electron-phonon coupling strength, or the new mass is 1 plus lambda or the old mass. So the mass gets heavier because typically this number is positive. Okay. So what is this number? Well, this number is a friend of this renormalization factor, and has to do with the derivative of the self-energy. So all these things can be calculated, and one can use them to understand how phonons are altering the band structure. Okay, so that's basically the what I want to tell you. And all of this, please note, has to do with how phonons affect electrons. Okay, so there's a whole other side of electron-phonon physics, which is how electrons affect phonons. So that would require a separate discussion that is quite detailed. So we're not going to do it today. So now I just want to show you an example of this kind of concepts with maybe let me just skip that. Going with an example with the perovskite I showed you yesterday. So I told you this is a system where people are interested in for various photovoltaic properties. So this is a calculation of the spectral function incorporating electron-phonon interactions. Okay, so in practice, here you see the valence band. Okay, there is a parabolic thing here centered at the gamma point. The gap is direct, so you also have a parabola in the conduction, and we start at 0 just to kind of for reference. The band gap is about 1.6 electron volts, but that's not very important here. So I'm not sure you can follow, but if you look at, there is a dashed blue line. I don't know if it's very clear on the screen. So there is this dashed blue line. So this is the calculation of the band structure using the FT, right? Then if you do a calculation of the spectral function, you get this kind of purple yellow structure. So at very low energy, they are very similar, so they are almost overlapping. Then they start deviating, and if you follow the maxima, you get the black line. Okay, so this black parabola actually is fatter than the original one. So that means that the effective mass has increased. All right. So now you can calculate how much the effective mass has increased, and that is something of the order of between 0.2 and 0.4, so like between 20 and 40%. So the electron is a little bit heavier than without electron-phonon interactions. So here, this lambda, you see there are two lines that I'm showing you here, and these two lines correspond to two different ways of evaluating this mass enhancement. So this is just a warning to tell you that when you go to in the world of many-body physics, there are many loose ends because there are several ways of doing calculations. Okay, it's not a variational approach like in the FT. So depending on the choice you make, you may get different values. In the case, for example, 0.2, 0.4. So one has to be very clever in making choices that are kind of comparable directly to experiments. So the other thing you observe in this picture is that, for example, here the bands are very sharp, but then after you exceed this energy, basically they blow up, and it's very broad and everything is defined everywhere. So you kind of lose the meaning of sharp bands, and you lose kind of quasi-particles. So what is happening here? If you follow the broadening of these things, that would be the lifetime. So you start at the conduction on bottom, so no broadening up to this point, and at some point it shoots up, and you have a constant broadening here. Okay, so this range here corresponds precisely to the onset of this purple region. So what is happening is that in this system, the characteristic phonon energy, which is basically the phonon that is most strongly coupled to electrons, is a longitudinal optical phonon about 10 millielectron volts. Okay, so this is the point basically where the system, so the electrons have enough energy to decay by emitting one of these phonons, and therefore at this point its lifetime is shortened dramatically. In this energy range, the electron does not have enough energy to decay, because if I were to remove 10 millivolts, I would fall in the band gap, but this is forbidden. Okay, so in a way, in this energy, this is protected from decaying, and that's why you have sharp sharp quasi-particles. All right. So all these effects are very typical in the world of electron-phonon interactions, and these are some of the things that you might see during this school. Okay. So with this, I want to close here and just to summarize three takeaway messages. So I think I wanted to try to convince you that the way to discuss electron-phonon physics systematically so without losing pieces, without making mistakes, is to use quantum field theory. Okay, there is language that has been worked on for 70 years, so we don't need to reinvent the wheel. Actually, we just need to study, papers and try to adapt the codes to take care of this kind of mathematical apparatus. The second thing is that the electron-phonon self-energy, so the middle self-energy, gives you a lot of information about mass normalization, quasi-particle lifetimes, and all these things. So that's, in a way, is the key quantity that we need for many problems related to electron-phonon physics. It's not all of it, but it's one of the essential bits. And one thing that I didn't describe, maybe I can just give you a quick slide here. When you calculate the lifetime using many body methods, you find some expression that is slightly different from the Fermi golden rule I discussed yesterday. Okay, so to get the Fermi golden rule, you need to make a few approximations to many body expressions. In particular, you need to replace the quasi-particle eigenvalue by the Kohn-Sham eigenvalue, and you need to assume that your quasi-particle has full quasi-particle weight, so you don't have any loss of quasi-particle weight. If you do that, you recover exactly the Fermi golden rule you get in density functional theory. Okay, so that is, in a way, is a lower level theory. Okay, that does not contain everything, but is reasonable. So in most calculations of transport, in practice, that is what is used. One could use the most sophisticated expression, but then one would have to explore all the implications of that, what happens, benchmarking against experiments, and that is another kind of complexity added on top of that. All right. So, but these things will have to be done at some point. So, and finally, this is a list of references. I'm not going to discuss them individually. I just want to say that some of this work actually is very old, but and that's actually where we learn everything that we know about these things. And it's really worth taking a look. They are really old papers, but they have a lot of physics inside. Okay, so these things got a little bit lost, but they're still essential reference for whatever we do in the world of electron-phonon interactions. Right. So this is the end of the lecture, and we can take some questions, maybe.
Thank you so much for your thoughts. Is there any, did we ever meet to consider a 4-point string constant for electron-phonon interaction?
So that has not been done ab initio. So I mean, one could. So when you go to that level, basically, the complexity is such that you need to use models, basically. So there are groups that are looking into that, but usually that is limited to either nearest neighbor interaction models, or like Holstein Hamiltonians, or maybe Fröhlich Hamiltonians, and basically we don't have ab initio quantitative accuracy. Okay, so we haven't done it, and I'm not aware of people in the ab initio, let's say, community who have done it. So that can become important when you start looking at high order correlations. Suppose you have electron multi-phonon interactions, or phonon multi-electron interactions. You have bipolarons forming and things like that. So those are very interesting, but I would say they're too complex, at least now, for practical ab initio calculations.
Thank you for this very interesting talk. And if I understand this correctly, it seems that all electrons in one formation are treated as scalar particles. So it's very difficult to generate to realistic half particle with arbitrary direction.
Oh, I think that should be fine. So what I showed here is just out of simplicity. I mean, this basically are it's basically collinear spins, if you want. The format is described. To do non-collinear, it should not be a problem at all. It's just a little bit, one has to be careful with the, the polymatrices. But it's, yeah, that I think should be totally fine.
Hi, thanks for the great talk. So you're on slide 13. You have epsilon to s. So what you've been describing is the exact excitation energy for an n+1 particle system. Excitation s. Why would there be an imaginary part?
Oh, that's basically, so what you want to imagine is I mean, I skip some steps, but basically that is representative of something like this, where that object will bring an imaginary part, basically. It's just a shortcut to say what would happen. So let's say a posteriori I could tell you, let's start from this and go back there, and let's assume that the self-energy has a real part and an imaginary part. Does that make sense?
Yeah, so it's not it's a constant thing versus a Dyson orbital thing.
It's basically, if you do the complete formalism, so this object is a complex function in general, okay? And in the simplest kind of representation, you could say this is basically a real part plus an imaginary part. And in that slide, yeah. Yeah, correct.
I think I'm sure when you consider electron-phonon calculation this to create phonon at non-vacuum particle. I'm sure it's some investment phonon example.
So there are, I think, there are two aspects there. So phonons, let's say all of the things I described, I mean, I didn't mention that, I mean, to get the equations, some of the later equations, one needs the harmonic approximation where you can describe phonons as independent oscillators, okay? If you go beyond that, the equation gets much uglier, okay? There are some theory papers that explore that, but they're not being translated into, let's say, computational methods because it gets really complicated. So that's basically phonon-phonon interactions. Then there is also an aspect of phonon-electron interactions where the phonon, you know, now let's say one can take phonons from density function perturbation theory. Those will be non-interacting in a sense, but one can still build interactions with the electrons using exactly the same language that I illustrated here, and there would be some self-energy for the phonons coming from the electrons essentially, and these things lead to lifetimes, lead to broadening and effects like that essentially. So all of this is doable.
One last question.
Thank you, very nice talk. So I just have a quick, more questions. Can you go to slide 8? Yeah, okay. So the equation in the last line. So the delta function is guaranteed to remove the self-flow interaction. The electron cannot take the same location. So, but how about the electron have different spin? Two electrons have different spin. They both can locate at the same location. So that because the argument R should also include the spin degree of freedom.
So this in this expression, R is the position variable, and this is the electron density. So you need to imagine that as integrated, so summed over the spin already. Okay, so this is the density of charge, right?
Yeah.
And
but if two electrons have different spin, so they can stay in the same location, right? They should have a non-zero position in the same location.
So the problem is that if you don't remove this interaction, basically you have 1 over infinity on this side. So this is actually an issue of the Coulomb interaction, not the spin. So this is 1 divided R minus R prime.
So if this triplet state, the two electrons have different spin, then two electrons can locate the same location. The probability is not zero.
I think you are thinking about orbitals. So if you have an orbital, so they can be in the same spatial orbital, okay? So this is not about orbitals. This is actually a position in space. So what cannot happen is that you have an interaction on the same point, because that will lead to an infinity, okay? So maybe let me say in a different way. So these actually, when you look at, for example, discuss things like Hartree-Fock or correlated systems, the same term is written kind of maybe more typically as a product of 4 field operators. So you have psi, 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 x prime, okay? So this is exactly the same. To get those 4 field operators, basically you need to replace 2 field operators here, 2 here, and express that in terms of field operators as well, okay? So this is exactly the same expression that people use in, when you have electron-electron interactions. It's just that in this form, it is more transparent where you have, why you have, the field operators in a certain order. And that is precisely because you have this delta function, okay? So basically, it cannot happen that, the same electron, so two electrons sit exactly on the same point, because that will lead to an infinite Coulomb interaction.
Yeah, but in some cases, in the environment, you have some Castle condition. You can remove the infinity.
I think, yeah, if you discuss orbitals and things like that, that's totally fine. But this is basically not about orbitals. It's just about, basically, if this term was not there, this expression would be infinity. That's the problem.